Conway's Base-13 function maps any real interval from a to b to the whole real line. That is, given any real interval a to b and any real number y, there will always exist some x within the interval a to b, such that the Base-13 function applied to x gives y. This is always true regardless of how close together a and b are. Not only that, the Base-13 function is discontinuous everywhere. The primary motivation for its discovery was as a counterexample to the converse of the intermediate value theorem, as we'll soon discuss. It seems that Conway never actually published the function, but it instead spread by word of mouth. The intermediate value theorem states that if a function f is continuous over some real interval a to b, then for any y which is between f of a and f of b, there exists an x between a and b such that f of x is equal to y. This is a way of mathematically capturing the continuity of the function, since there can't be any gaps or jumps along the curve f of x. To understand why the intermediate value theorem works, consider a discontinuous function. Here there is a jump where it's possible to find a value y between f of a and f of b such that there isn't a corresponding x value between a and b such that f of x is equal to y. And so the intermediate value theorem states that if f is a continuous function on the interval a to b, then given some y between f of a and f of b, there exists some x such that f of x is equal to y, and x is between a and b. This is often referred to as the intermediate value property, and so a shorter version would be all continuous functions satisfy the intermediate value property. The converse, or opposite, of the intermediate value theorem would say that if f is a discontinuous function on the interval ab, then there exists some y between f of a and f of b, such that there does not exist some x, such that f of x is equal to y, and that x is between a and b. That is, this will always happen with discontinuous functions. In short, there is no discontinuous function which satisfies the intermediate value property. In this video, we'll show that the Base-13 function satisfies the intermediate value property, but is discontinuous everywhere, making it a counterexample to the converse of the intermediate value theorem. There is one catch, however. We do have to work in Base-13. We're used to working in Base-10, where we have 10 digits, 0 to 9. In Base-13, we introduce 3 more digits represented by A, B, and C, after which the cycle repeats, going through 10, 11, 12, through to 1A, 1B, and 1C, until you get to 20, and so on. For decimals, the case is slightly different. In Base-10, the numbers ranging from 0 to 1 in steps of 0.1 differ by 1/10. But in Base-13, they differ by 1/13. We're now ready to introduce Conway's Base-13 function. First, consider a real number in Base-13, x. If at some point we find a sequence of digits which start with a, then a sequence of digits 0 to 9 will denote x1, x2, x3, and so on, followed by a c, and then after c, all digits, potentially out to infinity, are 0 to 9. We'll denote y1, y2, and so on. Then we call this a type A number. Similarly, if we have a number which at some point has a sequence of digits starting with b, then a sequence of digits 0 through 9, then a c which is followed by only digits 0 through 9, then we call this a type B number. These sequences which define type A or type B numbers are called type A or type B tails. The Base-13 function is a conditional function where if x is type A, we take the digits in between a and c and make them the integer part of the output, and the digits after c become the decimal part of the output. Because we defined all these digits to be 0 to 9, the output is just a regular Base-10 number. With type B numbers we do the same, but this time we take the negative value of the output. Any other number is mapped to 0. Let's go through some examples to get a feel for the Base-13 function. Here we have a type A number with 1, 3 between A and C, followed by a 7, so this maps to 13.7. Notice how we started with a base 13 number and finished with a base 10 number. If we take the same number and change the A to a B, we get a type B number. We still have the 1 and 3 between B and C, followed by a 7, so this maps to minus 13.7. I want to now demonstrate the discontinuous nature of the function and how small changes in input can lead to large differences in output. Take this number for example, which maps to 10.11. If we insert a 0 at the 6th decimal place, it hardly changes the number at all, but the output will be 10 times larger. Plotting the function for all numbers between 0 and 1 to 4 decimal places, we see firstly that most, unsurprisingly, are neither type A nor type B, and so map to 0. We then have a sequence of type A numbers of the form 0.A, x2, c, x4, where x2 and x4 take values 0 through 9, and a similar sequence of type B numbers straight after. If we increase the number of digits to 5 decimal places, we get a wider range of behavior. We still have the type A numbers at 0.A, but this time the extra decimal place means we now have a range of 0 to 100 on the y-axis. This is still followed by the type B numbers at 0.B. But this time there are these smaller sequences where the first digit is fixed, in this case at 1, but remember the x-axis is in base 13, so the first digit could be any of 0 to c. This is then followed by either a type A or type B tail. We also have the appearance of new sequences at 0.A, where this time there is only one digit between A and C, and 2 digits after C. There's also a similar version, but of type B. From here, increasing the number of digits increases the range of values the base-13 function can take anywhere along the x-axis. The fact that most of the values are 0 doesn't stop the function from mapping every real interval to the real line, as we're now ready to show. Between any two numbers, a and b, there exists some x such that f of x is not equal to 0. We'll show this to be true, but not only that, we can make f of x equal to whatever we like. First, take any interval a to b. Assume, without loss of generality, that b is greater than a. A and b can be as close together as we like, but at some point we'll find a decimal place where they differ. And so if we create a new number x with the same digits as a, up to and including the first digit it differs from b, then make the next digit, which is less than c, a c. This guarantees that x is greater than a and less than b. After that, we're free to add a type A or type B tail which maps to whatever value we like. In this case, I've added a tail which maps to 1.01. And so because the base-13 function maps any interval a,b to the real line, any y value we choose will always have a corresponding x within the interval. This means that the base-13 function satisfies the intermediate value property, and so disproves the converse of the intermediate value theorem. Thanks for watching. I'll see you next time.